Hey everyone, welcome to the question show. Your questions, my answers. As always, wherever you are across my channel, if a question pops into your brain, just write it down. I will gather them up and I will answer them here. Now, I am recording this question show on Monday, May 3rd, 2021. So I keep saying that maybe next week Starship SN15 is going to fly or explode or both. And it still hasn't happened at the time that I'm recording this, but who knows what other interesting things are going to be happening this week that I failed to report and that Chad will hilariously put in as a background while I'm talking. But yeah, so if you want to join the show live, you can just join me every Monday at 5 p.m. Pacific time on my YouTube channel. And I'm happy to answer questions and we can do the back and forth and follow-up questions. And the show is actually about twice the length of what you see. So if you want to join live, you totally can. Otherwise, enjoy the fancier version with all the graphics and such. All right, let's get into the questions. John Ackerman. We're not the first intelligent species in the universe. Just because we don't see any others is due to the fact that we are not sufficiently intelligent to recognize them. All right, in our long-running Fermi paradox, great filter conversation, the conversation continues. And so I guess this argument you can say is, we hear this a lot, which is that we are not sufficiently capable of even observing alien species. They could be all around us all the time and we wouldn't even know. And so, there's sort of two parts to this. The first part is like, just because something isn't intelligent doesn't mean that it doesn't know you're there. So like an ant isn't very intelligent, but it will gladly bite you. An ant sees you as a threat, challenges you for resources, will give you a nip if it needs to. It's really painful. So even though they're not very intelligent, they can recognize and see that you're there. And so we would have the same thing. I mean, we're not very intelligent relative to some incredibly intelligent galactic species that has mastered space and time. But if they're interacting with the matter or the energy in the universe in some way, we can see it. We can watch as stars wink out of existence because they've enclosed them in Dyson spheres. We can watch as their spaceships glide past as they build their interstellar superhighway. So that argument doesn't really hold as long as the laws of physics apply to them in the same way that the laws of physics apply to us. Now, you can sort of take us to this next level where that there's some other existence, some other reality, some transcendence that aliens go through where they stop existing in this universe using matter and energy and move on to some other existence that we can't perceive. And sure, yeah, maybe. But I mean, like an alien civilization that doesn't interact with you in any way that you can't perceive, that sounds like dark matter. like at a certain point, it doesn't matter. It's as if it doesn't exist, if it's not in any way, shape, or form going to impact your existence at all until you make this transition. And then you can sort of imagine all of the species that are in between, the ones who are like us. They formed in the universe out of organic elements near a star. They formed multicellular organisms. They built technology. They built spacecraft. They created a solar system and eventually galaxy spanning civilization. We would see them until they finally transcended to the next plane of existence and disappeared and left behind their artifacts. So I don't really buy that. Even if they're smarter than us, we're smart enough to just perceive them unless they're not like us in any way, shape, or form, and then they might as well not exist, and then who cares? So, Ali Saeed. Question, why don't I ever see sponsor shoutouts in your videos? Many of my other favorite YouTubers have sponsorships from Brilliant, CuriosityStream, Nebula, etc. That's a good question. That's because I'm not a YouTuber and I don't make my money from YouTube. I have some ads on YouTube, but the only reason I have ads on YouTube is so that I don't have more ads on YouTube. So where we're at right now with YouTube is that if you don't put any advertisements on your YouTube videos, then YouTube will put ads on your YouTube videos aggressively and take all the money. And so if I put just whatever's the minimum amount of ads, one ad right at the beginning, then it stops YouTube from putting additional ads and And that's sort of the compromise that I've been able to figure out. But the bottom line is that I'm not a YouTuber, right? I'm a publisher of a website, and that's my business. And so I'm advertising through this entire thing. Right? I'm mentioning that I'm the publisher of Universe Today, that you should come and check out Universe Today, and you should sign up to the Universe Today newsletter. And how about the Universe Today podcast and also Astronomy Cast with my co-host, Dr. Pamela Gay. And also every week we do the weekly Space Hangout. And all of those are advertisements for Universe Today. And if you come to Universe Today, we have advertisements there, and I'm able to pay the writing team. So, I'm not a YouTuber. And so it's just like, it's not worth, like, doing sponsored stuff on YouTube is hard, and I don't like it. It's like you have to you have to negotiate the contract, and you have to send a quote, you have to send an invoice, you have to follow up, and you have to, like, it's a lot of work, and I don't want to do it. So I'm happy with sort of the way we have things set up with Universe Today, and the revenue is great. Allows me to hire the team and do the work and have a job. We mentioned this a couple of weeks ago, and I'm good. So yeah, the more money I could make, the less advertising I would try to run. I'm much more interested in making the content as accessible as possible than trying to make as much money from it as possible. Logic on abstractions. Hey, Fraser, let's say that I'm a technological civilization on one of the closer-ish stars to us. What kind of a telescope would I need to be able to detect our light pollution? I assume they need at least 1 pixel of the Earth. Yeah, well, so the job of detecting light pollution, we're sort of imagining this technological civilization like Earth that is generating chlorofluorocarbons and other industrial pollutants that would cause this really strong signal that there is a technological civilization. I mean, if you see chlorofluorocarbons in the atmosphere of a planet, there's really no natural process that can generate that. And so you could say, oh, wow, there's a civilization there, and they just started to ruin their ozone layer. So what would you need to be able to detect that? Well, the first thing is that you need to be able to detect the light from the planet separate from the light of the star. And we actually talked about this with Jesse Christensen earlier this week, that you need a factor of billions between the light of the star and the light of the planet. So as long as you can block out the light of the planet with your coronagraph or your star shade, and you're able to get the really faint light of the planet separate from it, then you need to have a really powerful telescope that lets you really brighten up that 1 pixel that you're getting into a rainbow. And so you're creating, I'm sure you've seen this spectroscopic analysis of various stars. And this is the way that scientists can take a star and they can know what some of the chemicals are that are in that star by the rainbow that they're able to create. And so you need to be able to create a rainbow of that 1 pixel of the planet. And that will tell you the chemicals that are in the atmosphere of that planet. Needless to say, you got to block the light. That's hard. You got to be able to get enough light coming into your sensor so that you can create that analysis of the atmosphere. But yeah, 1 pixel will do the trick. It just has to be 1 really, really good pixel. Dustman, are there any scientific examples of energy turning into matter? Yeah, absolutely. Sort of. So the best example that we have of energy turning into matter is our particle accelerators. That's actually what's going on in like the Large Hadron Collider and some of these other big particle accelerators. Is you've got these particles that don't have a lot of mass, protons, electrons, whatever, and you spin them around this giant ring faster and faster and faster until you're going, say, 99.99999% the speed of light. And that imparts an enormous amount of momentum into the particle. And then you're crashing these particles. You're crashing 2 beams of these particles into each other. And then what you've got is you've essentially got, when they're crashing into each other, you've got an enormous amount of energy that is in a tiny, tiny space because you've got all of this momentum that's caught up in these particles. And so when these particles crash into each other, you've got all this energy, and there's so much energy that the energy has to go somewhere. And what the energy does is it turns into particles, and the particles just start popping out because you can't have that much energy in that dense of an area. And so literally what the Large Hadron Collider is doing is it is turning energy, the electricity of accelerating these particles to go around this particle accelerator, into matter, into additional particles that are spraying out of this place, this dense spot where particles are crashing into each other, energy is being released, and yet it's too dense, and so new particles have to be formed, which is kind of amazing. Joe, how do we measure the age of rocks and meteorites? How do we measure the age of our solar system and others? So one of the questions that scientists wanted to know was, how old is the solar system? It's really hard to figure out the age. Here on Earth, the way we can sort of determine the age of things is we use this technique called radioisotopic dating, where you take some element, say uranium, ones that have a very long half-life that decay very slowly into other chemicals, atoms, and then you measure the ratios of the one, I guess the one that then is going to decay into the other. And you know how quickly this decay happens. And so when you find a sample, you measure the pre-decay, the post-decay, you figure out the ratio, and that tells you how old this rock is. And the problem is, here on the surface of Earth, there's weathering going on all over the time. There's subduction going on of the plates. Various parts of the planet are being hidden. Other parts are being revealed. And so you can't find here on Earth parts of rock that are as old as Earth itself. But astronomers were able to do the same technique on meteorites that have fallen from space. And what they found when they used this technique is that every single meteorite has the same age. They're all 4.54 billion years old. And so far, like every single one of them. So it tells you that all of the planets, all of the rocks, all of the asteroids, comets, etc., in the solar system all formed at the same time out of the same raw material of the various elements that came together, and then everything started to age at the same time, which is kind of amazing. Which means that if we ever do find a meteorite and we do radioisotopic dating, and it is like just a completely different age, like 8 billion years old, or even 6 billion years old, it would mean that it came from another star system, that it was an interstellar meteorite. And they're around. They've got to be. I mean, we've seen Oumuamua, we've seen Borisov. And so the best idea to try and find these is to go to the moon and actually look on the surface of the moon. That if you drill down in the moon and you bring back samples, then you could find particles in the moon regolith that came from outside the solar system, embedded inside. So it's one of the really big reasons why to go back to the moon. I know that wasn't exactly your entire question, but I sort of kept going because I think it's so cool. Arjun, now that we know MOXIE works, will the next MOXIE be able to make O2 for the future Mars mission? What other proof of concepts will be needed for a Mars mission? It's fantastic. MOXIE, for those of you who don't know, this is this cool experiment that was attached onto the Perseverance rover, and its only job was to demonstrate that it could bring in carbon dioxide from the atmosphere of Mars, convert it, and be able to produce oxygen that then, say, astronauts could breathe, or it could be merged with hydrogen to create water, or you could use it for propellant, for all kinds of things. And I think they only made like a couple of grams of oxygen, enough for an astronaut to breathe for like 10 minutes. But it was a proof of concept. It showed that you could take a much larger machine, set it up, have it run for a longer period of time, and produce significant amounts of oxygen on the surface of Mars. And that's just one example of this idea of in situ, that you are making the material to survive, to get back, return fuel, food, water, everything on site, as opposed to having to cart everything from home. What else will need to be done? I mean, there's literally 1,000 of these tiny little proofs of concepts that need to happen. We need to think about, say, the health of astronauts. We need to think about their psychology. We need to think about every part of a closed system of scrubbing away carbon dioxide. So it's like, just sort of think about this, like on the space station, they have carbon dioxide scrubbers, and they use up various kinds of elements to be able to do that. They have lithium hydroxide as one. So you're going to need to maybe eventually make your own carbon dioxide scrubbers to be able to, right? Like just everything. your own water, your own food, your own fuel, your own growing material, building material, radiation shielding. Like it just goes on and on and on. But the more of this stuff that you can figure out and build on the surface of Mars, then the more successful you're going to be, the less material you have to take from Earth. It would be amazing. I'm sort of imagining something like Factorio, where you send some robot spacecraft that has a bunch of these little machines on board, one to make oxygen, one to try and extract water from the atmosphere for various uses, one which can maybe bring in regolith and heat it up and spit out metals and various other compounds that can then be ready to go when the astronauts get there. It's a great idea. So this is just one tiny little step. And it sort of shows you that if SpaceX is successful and they are able to send humans to Mars by 2024, 2026. That's great. You know, you got people just stumbling out of the Starship out onto the surface of Mars. But now you got all these other details to keep them alive because Mars is trying to kill them. So yeah, I think it's really exciting that this experiment is on the rover, and I would love to see many more of these. I'd love to see like a lander that has like 20 technologies on board to try to test out all of these little pieces. Maybe that's something we'll see in the future after Perseverance has demonstrated that this really works. More questions in a second, but first I'd like to thank our patrons: Robert Berkovich, Peter Erickson, Daniel Duarte, Trevor Jobling, Gordon Chin, and the rest of our 826 patrons for their generous support. Want our videos early with no ads? Join our community at patreon.com/universetoday. William R., do you think it's possible to significantly extend the life of the sun and by extension Earth, possibly even turn it into a red dwarf? I mean, we're going to need to consider the word possible, practical. So first we'll talk about sort of what's going on. So the sun is heating up. And the reason the sun is heating up is that in the core of the sun, you've got hydrogen turning into helium. And this helium is building up in this shell around the core of the sun. And as it does this, it sort of expands the sun out a little bit and increases the overall amount of luminosity that's coming out of the sun. And what that means is the temperatures here on Earth are going to rise and rise and rise over the next 500 million to a billion years. It's not causing global warming, has nothing to do with global warming, but in a billion years, it will become so significant that it boils the Earth's oceans, essentially makes survival on the surface of Earth impossible. So what do we do about this? The one idea is that we move the Earth. So if you got like an asteroid that was on some kind of conveyor belt in between the Earth and Jupiter, and it did one orbit past the Earth and then flew out and did a slingshot around Jupiter and then came back to the Earth. And as long as it did it about once every 10,000 years or so, you could be stealing orbital energy from Jupiter, giving it to the Earth, and that would cause the Earth to slowly move out on its orbit at the same rate that the sun is heating up, and so the temperature of the Earth would always remain the same. So that's one way that we could save the Earth all the way through until the sun turns into a red giant. We would be eventually getting pretty close to Jupiter, but it would do the trick. Could we do anything to the sun? So the problem with the sun is that because it's a main sequence star, the sun has this core that is, where all the fusion's happening. And then around that is the radiative zone where it's not hot enough and dense enough to have fusion. And so all of the gamma radiation that's created in the core has to random walk its way through this zone. And the outer part is the convective zone. And that's where the sun is more like a lava lamp. And you get these blobs of hot gas that are able to rise and fall like boiling water. And as they rise up, they reach the surface of the sun and they bloop, and they let out their energy into space, and then they cool down and they drop down to the top of the radiative zone, pick up more energy and go back up. And so because you've got at the outer area, you've got this nice convective area. And then in the core, you've got all the fuel that's being burned by the sun, but you've got this shield, the radiative zone. the sun will die when it runs out of fuel in the core, even though there's vastly more hydrogen that's still available to it. It just can't use it because it's just not mixing. But if you're able to decrease the mass of the sun down to about a red dwarf, suddenly the entire star would become convective. So the reason that red dwarf stars are so long-lived, one, because they just are burning hydrogen at a far less rapid rate, but also they're fully convective. They just use up all the hydrogen very efficiently. And so the goal would be to turn the sun into a red dwarf. Actually, multiple red dwarfs. You'd probably need to turn it into like 8 red dwarfs would do the trick. So you could break the sun into 8 pieces. Each one would be a red dwarf, and then they would all last for 10 trillion years, and they wouldn't really change that much. And so the question is, how do you do it? So there's a couple of ideas that have been proposed. One is that you create a really powerful magnetic field at the surface of the sun. You do this thing called stellar lifting. You're essentially funneling material with your magnetic field off of the sun, drawing it away, and then gathering it up in some other location to create another sun. And then you draw off more and you create another sun, you draw off more, you create another sun. And then there's other ideas that you could try to essentially increase the solar wind from the sun. You could sort of boost up the solar wind. It would be letting off a lot more of its own material off into space. And you just let it sort of shrink down to the point that it was a red dwarf, and then it would last a lot longer. But none of those are practical. None of those ideas are really practical. It's sort of in theory, but who knows? In 500 million years, maybe we'll become a technological civilization capable of being able to do that kind of a thing. Raza Siddiqui. Is it time to map Mars? Who would settle where to avoid wars? Well, Mars is well mapped. Thanks to NASA's Mars Reconnaissance Orbiter, vast chunks of Mars have been mapped down to a resolution of about 1 meter. So we have very, very good maps of Mars and the capability to produce even better maps. So the mapping part isn't really a problem. Now, right now, the settlement, I'm making air quotes here, of Mars falls under the Outer Space Treaty, which is that you can't. You're not allowed to colonize, own, declare any territory on Mars at all. You can build a research station on Mars if you want, and I guess you could classify a city of 1 million inhabitants as a research station. But if at any point any nation on Earth claims Mars, the other nations on Earth are going to have something to say about it. And that nation is going to suffer all kinds of penalties here on Earth for making that kind of a claim. And then, yeah, maybe they're going to have to fight a war here on Earth over who owns Mars, which would be terrible. Now, you could imagine that Elon Musk just says, I'm just going to colonize Mars and I don't care what you say. And if you try to stop me, too bad. But I mean, his day-to-day operations require Earth, all of the material to build starships, all of the people, all of the rocket fuel, the operations of his company. Like, there's so many ways that regulators could stop Elon Musk from doing what he wants to do to create a giant city on Mars and claim it. But as they say, possession is 9/10 of the law. And so if Elon Musk is able to sneak out a robotic factory and a group of colonists and a starship and to go to an asteroid or even to Mars, and they're able to survive without any issues back here on Earth, then there's kind of nothing we can do to stop them, unless someone wanted to send a military to Mars to make them leave. I don't know. So I wouldn't really worry about it. I think by the time you get to a point where people are having serious conversations about who gets to live on Mars and how, you're going to see new versions of the Outer Space Treaty be able to set that out. And so we'll see what happens in the future. But right now, you're not allowed. Morpheus Dream. Everyone has been talking about the infrared telescopes, but is there a reason to have an ultraviolet telescope? Sure. Yeah, there are a bunch of ultraviolet telescopes out there. In fact, the Hubble Space Telescope can see from the infrared through the visible light to ultraviolet, and there are a lot of other specific ultraviolet telescopes. The challenge is for certain wavelengths of ultraviolet, you need to be out in space. You can see some ultraviolet from here on the surface of the Earth, but to see the entire wavelength. You want to be out in space. So what do you do with ultraviolet? Well, ultraviolet rays are generated by hot things. Very energetic things. So newly forming stars, young stars, like the biggest stars that are out there, things that have had a supernova explosion, things that have collided with each other. So there's plenty of really good reasons to observe the universe in ultraviolet, and a lot of really interesting astronomy is done that shows it. And there's some wonderful pictures where they'll take some images from Hubble and then they'll overlay that images from an ultraviolet instrument to show you the different parts of the sky that are revealed when you look in these different wavelengths. Just like, if you could imagine sort of running through the entire wavelength and observing the same object. The sun, for example, the sun is giving off radio waves. You could detect that and it would tell you things about the sun. The sun is giving off infrared. You can detect that. It's telling, the heat. You can tell certain things about the sun. The sun's giving off visible light, obviously, the photons, etc., that we can see with our eyes. The sun is giving off ultraviolet. That tells us other things about the sun, different regions. When you see a flare, they want to image those in ultraviolet. The sun is giving off X-rays. And again, with flares, they're giving off really high energy explosions. You can see those in ultraviolet and X-rays. So there's plenty of really good reasons to view the sky in ultraviolet. There's good reasons to view the sky in every single wavelength of the electromagnetic spectrum. Strange quark star. What are the immediate uses for Starship's 100-ton capacity for low Earth orbit beyond Starlink stacks and ride shares, seeing as even the heaviest spacecraft spy satellites never exceed 20 tons? Well, right now, the size of satellites is mostly dependent on the size and capability of the launch vehicle. And so a lot of people design their payloads around this. They're anticipating, if you're going to launch a military satellite, you're going to pay $400 million for your launch. And you've got to have your satellite fit within a 5-meter fairing. So what do you do when your launch costs $10 million or maybe $1 million and it fits within a 9-meter fairing and it could be 100 tons? We don't know what we're going to use that kind of launch capability for. And it might be, as Elon Musk thinks, it's going to be used for sending humans to Mars and all their stuff. But maybe it's going to be that we're going to finally, space power will be something that we can actually make money with. Or maybe finally asteroid mining will make sense. We just don't know. A lot of the times, we don't know what the benefit is going to be from the infrastructure that we're creating. You just bring the infrastructure. We didn't know all of the uses of the highway system in the United States and Canada. And yet, once they were there, suddenly new ideas started to form, new networks were created, new opportunities were formed. And that's what an entirely new launch system is going to be. So right now, yeah, you're right. It's going to be a bunch of Starlinks. There's going to be the existing launch queue of satellites, and then people are going to go back to the drawing board and come up with new ideas for what you can do with a spacecraft capable of lifting, more than 100 tons to orbit, of refueling in space, flying to the moon, landing, returning, flying to Mars, making fuel on the surface of Mars, returning to Earth. We don't know. That's sort of what comes next. Ricardo Favas. Can we match other stars' velocity with current technology, or can we just do flybys? That's actually a really great question. And I think it's because a lot of people don't really think this part through. When you think about that you want to send an interstellar mission to some other star, you're sort of envisioning that you're stationary and you're firing your spaceship off to some other star and it's stationary, and then your ship is going to arrive, it's going to do its deceleration burn, it's going to get to the destination star. But the reality is that the sun is moving on an orbit and the destination star is going to be moving on an orbit. It could be moving in the same direction in the Milky Way. It could be moving in an opposite direction. It could be moving up. Can move in all kinds of ways. And so when you're choosing a destination for your interstellar probe, you're going to want to take all of that into account to find a star that you can, when you think about how the orbits of the planets go around the sun, you've got Earth and Mars, and you do this very specific kind of orbit where you increase your orbit from Earth and then you meet Mars at the sort of the high point of your orbit, and you go into orbit around Mars. And you're going to want to do something similar. And so a flyby is easier because you don't really care what the velocity of the destination is. You just fly at the most reasonable direct path, one that crosses your pathway with the star at the right time, and you take a bunch of pictures and then you fly past. But if you're going to try to go into orbit or into that star system, then you need to find one that's moving in the right direction with you so that you can do a very similar kind of maneuver to arrive there. It's going to be trickier, but I mean, both are going to be really tough. Mystic City. Do we know if the expansion rate of the universe fluctuates, and do we even have a rate in the first place? So this is one of the most incredible discoveries in astronomy. And this was the discovery made by Edwin Hubble back in the 1930s, where he measured the expansion rate of the universe. And this is this thing called the Hubble constant. And he measured it was roughly 70 kilometers per second per megaparsec, I think is the numbering. I may have some units wrong there, I apologize, but it's gigantic numbers, which means that every second that goes by, stars are moving farther and faster away from each other. And every second goes by, they're moving faster from each other and faster and faster. And so you're getting this expansion. And over time, astronomers have been trying to pin down this exact Hubble constant. And they have figured out various times and ways that they can measure the expansion rate of the universe. If you measure it really early on in the universe in the cosmic microwave background radiation, or you can measure it using the same technique that Hubble did almost 100 years ago. And when you do that, you actually get two different measurements. They're similar-ish, they're roughly around 70, but they're different enough and their error bars don't overlap. And so astronomers, one of the they call this the crisis in cosmology. Astronomers are trying to figure out what is the expansion rate of the universe. And it's possible that the expansion rate of the universe has been shifting over time. We know that there is this additional acceleration that's coming from dark energy that is accelerating the expansion of the universe. But even after you take that into account, it's weird that these two numbers don't agree with each other. And so it might mean there's new physics that we don't understand, or it might just be that there's just some mistake in the measurement, although the measurements are really good at this point. So it's one part where we just don't really know the answer right now. So to your question, we don't know if the expansion rate fluctuates. We think that the expansion rate is speeding up. It's accelerating thanks to dark energy, but maybe it went faster and slower and faster and slower at different times in the universe, but we don't know. All right, those are all the questions this week. Thank you, everybody, for asking them. Of course, if you want to ask your questions live, you can join me every Monday at 5 p.m. Pacific time here on my YouTube channel, or you can ask your questions, put it into any video, and I'll gather a bunch of them up and I will answer them here. We'll see you next week. If you want a single comprehensive resource for space news, you'll want to subscribe to my weekly email newsletter. Every Friday, I send out a magazine of space news with dozens of stories, pictures, brief highlights about the story, and links so you can find out more. Go to universetoday.com/newsletter to sign up. It's totally free. And did you know that all my videos are also available in a handy audio podcast format so that you can have the latest episodes as well as special bonus material like interviews with me show up on your audio device? Go to universetoday.com/audio or search for Universe Today on iTunes, Spotify, or wherever you get your podcasts. And I'll put a link in the show notes. Thanks to all the moderators, and a special thanks, as always, to Chad Weber and Nancy Graziano.